All right, so we're going to finish section 1.6. I want to try this equation here. So we're going to try to solve this equation for the variable t. Okay. And it's a messy looking equation. It's very complicated looking. All right. Well, what I'm going to do is zero the equation out first by taking the 12 over to the left side by subtracting 12 from both sides. All right. And now, ladies and gentlemen, we should be able to see hopefully the forest for the trees here. We can see that in general, we have a quadratic form equation. This is said to be quadratic in form. I didn't say quadratic equation, I said quadratic form equation. In the sense that we have like factors here of 2 plus 3 over t, and the leading degree is twice the middle degree. And anytime you have that construct, you have a quadratic form type construct. And with a u substitution, you can reduce this down to an ordinary quadratic equation. So what I'm going to do is I'm going to let the variable u be equal to this guy right here, 2 plus 3 over t. And if that's the case, then this would imply then that u squared is going to be equal to 2 plus 3 over t quantity squared. Now, having made my u assignment here, I'm going to make my u substitution and reduce this quadratic form equation down to a quadratic equation in the variable u. So this term is going to be replaced with u squared. This is going to be replaced with u. And then we have a very trivial equation in the variable u to solve. That's the intention of a u substitution, which are used in higher level math. Calculus makes use of u substitutions all the time to help you see the forest for the trees. All we got to do now is solve this equation, this much simpler looking equation in the variable u. It is a quadratic equation. And we are able to solve it by the factoring method. It's very easy to factor this trinomial. Two factors of negative 12 that sum up to negative 1. The middle coefficient are negative 4 and 3. So this immediately factors into u minus 4 times u plus 3. Now we're going to set both factors equal to 0 and then solve the equations for u. Solving this first equation, we get u is equal to 4, and then this one gives us u is equal to negative 3. Now, this is very important. We were not asked to solve for the variable u. We were asked to solve for the variable t. So it is now very important that we back substitute what we let u be equal to. So I'm going to have to bring back 2 plus 3 over t and replace this u with it and this u with it, because that's what we assigned u to be equal to way back up here. So therefore, I replace u with 2 plus 3 over t. And then I'll have to solve this equation for t. And I got to replace this u with 2 plus 3 over t. And then I'll have to solve this equation for t. To solve this equation for t, I'm going to subtract 2 from both sides, in which case I have 3 over t is equal to 2. And then it is a rational equation in the variable t. We could multiply both sides of the equation by t to get rid of this fraction here. But you got to multiply the right side by t also. And so therefore these t's drop out. We're left with 3 is equal to 2t. Now we solve for t by dividing both sides by 2. And we discover that one solution to our original equation in t is 3 halves. So that's one solution, 3 halves. Now we solve this other equation for t again by subtracting 2 from both sides. Multiplying both sides by t. Dividing both sides by negative 5. And ladies and gentlemen, we have our other solution for that equation. And so we're done. So a u substitution is highly recommended here to transform a very nasty looking equation into a very simple equation. And then once you solve it for u, you just got to remember to back substitute and bring back what you let u be equal to. And then you can solve for the original variable you're asked to solve for. All right. Any questions how we tackled solving that equation by using a u substitution? U substitutions are used all the time in calculus to help you simplify complicated situations. into simpler situations or even trivial situations in some cases. So that's a classic U substitution. Any questions about that problem there? All right, I want to solve another one, somewhat similar to that, but a little different. 30 times k to the negative 2 power minus 23 times k to the negative 1 power plus 2 is equal to 0. We want to solve for k, but this is rather messy looking. In fact, it's very messy looking. You are welcome, ladies and gentlemen, to use a U substitution here because we do have a quadratic form equation in the sense that this degree is twice the middle degree. Anytime you have that situation where the degree of the leading term is 2 times the degree of the middle term, you have a quadratic form situation here. So this equation is quadratic in form. Therefore, by utilizing a U substitution, we can reduce it down to a simple quadratic equation. Just let U be k to the negative 1 power. So U is equal to the k to the negative 1 power. That would imply then that U squared has got to be equal to k to the negative 2 power. Let's make our substitution and reduce this down to an ordinary quadratic equation. So therefore, we're going to have 30. Replacing k to the negative 2 power is U squared. Replacing k to the negative 1 power is U. And this now is the equation that we have to solve in the variable U. And it's a much nicer looking equation. This is a quadratic equation. Are we able to factor this left side of our, are we able to factor this left side here? Well, you can use the quadratic formula or you can use the grouping method. It's up to you. I don't care how you factor this. We just got to get this factored one way or another. All right. And so the way you go about solving this equation, I'm going to leave it, up to you. If you don't want to factor this trinomial, which would require the grouping method, since it's a difficult trinomial, you could use the quadratic formula if you want. Maybe we could try the quadratic formula. My A is equal to 30. My B is the linear coefficient of negative 23, and my C is the constant term of 2. So here we go. We'll use the quadratic formula, which would be the opposite of B. So it's going to be the opposite of negative 23, plus or minus the square root of B squared minus 4 times A times C. And this all sits over 2 times A. All right, and so now we just have to crank out these two solutions. By simplifying this, we have 23 plus or minus the square root of. This is called the discriminant, and I did include a very short video describing how the discriminant can help us predict what type of solutions to expect for a quadratic equation. Make sure you do get a chance to watch that short video that I did post on Canvas, and I did email all of you indicating its availability. Anyways, if we get on our calculator and dial this up, what does this become? All of that. It should become 289. So this is 289. And this all sits over 60. Now, because my discriminant is a positive number, that indicates that the solutions to this quadratic equation in the variable U are going to be real solutions. They're not going to be imaginary or complex. If the discriminant is negative, then you would have complex conjugate solutions where you would see I. Furthermore, this happens to be a perfect square. And since this is a perfect square, we're going to be able to get rid of our square root. And so therefore, the solutions to this quadratic equation in a variable U are going to be real rational solutions, meaning you're not going to see your square root. If this was a positive non-perfect square number, then your solutions to such a quadratic equation would be real irrational solutions where the square root would hang around in your final answers. But the square root's about to go bye-bye here because the square root of 289 is 17. Therefore, U is going to be equal to 23 plus or minus 17 all over 60. So we're going to have two possible solutions for U. U could be equal to 23 plus 17 over 60. And the other solution would be 23 minus 17 over 60. 23 plus 17 is, I believe, 40, and 40 over 60 reduces down to 2/3. There's one solution for you. 23 minus 17 is 6, and 6 over 60 reduces down to 1/10. There's another solution for you. Okay, so we found our two solutions for u. U is equal to 2/3, and u is equal to 1/10. Are we done? The answer is no. Why not? Well, because we were not asked to solve for u. We were asked to solve for k. Okay, and so now, ladies and gentlemen, we have to back substitute. Back in for u, I must bring back what I let u be equal to, which is k to the negative 1 power. So therefore, this would imply then that k to the negative 1 power is equal to 2/3. Likewise, k to the negative 1 power is equal to 1/10. And now we have to solve these two equations for k. Well, k to the negative 1 power being equal to 2/3 is implying that we have 1 over k, because k to the negative 1 power is 1 over k. So 1 over k is equal to 2/3. To solve for k, the simplest way to do this is just to reciprocate both sides of your equation. So therefore, k is equal to 3/2. There's one of your solutions, 3/2. Solving this other equation, k to the negative 1 power is equal to 1/10. Is implying that we really have 1 over k is equal to 1/10. Reciprocating both sides implies that k is equal to 10. Ladies and gentlemen, we're done. We have our two solutions, or our solutions to the original equation in the variable k. So the two solutions for this equation are 3/2 and 10. And we showed you how to get those solutions by implementing a u substitution. Any questions about that u substitution? So u substitutions are designed to take a nasty situation and turn it into one that looks simpler, easier to deal with. Okay, that's the intention of a u substitution. All right. Just wanted to demonstrate a couple of those there. So whenever your equation is quadratic in form, where this degree is twice the middle degree, you can use a u substitution to reduce it down to an ordinary quadratic equation. And then, but don't forget in the end to back substitute and bring back what you let u be equal to recover the original variable that you were being asked to solve for. Okay. All right, the only other thing in this section before I close the door on it is solving a couple of formulas for requested variables. Let's solve this one here. This formula here will give us, it pertains to the electrical world. If you're designing an electrical circuit, we would have 3 resistors in parallel, R1, R2, and R3, and this formula is designed to compute the equivalent resistance of the circuit. A resistor is a component in an electrical circuit that basically reduces the voltage, okay, and provides a voltage drop across it. Resistance can be good or it can be bad. If you're trying to cook a piece of toast in your toaster, then you want high resistance, so you have heat to cook your toast. That's where resistance is good. Resistance can be bad, however, as it could cause a wire to heat to a point where it could actually start a fire. So you got to pay attention to your resistances in electrical circuits. Anyways, we're going to take this formula here and we're going to solve it for R3. We're going to solve it for this resistance here. Okay. How do we solve for R3? Well, that means we got to get R3 all by its lonesome on one side of our equation and everything else on the opposite side. To do that, this is a rational equation. So I'm going to, first of all, find the least common denominator. And what would be the least common denominator of all these denominators? What are we going to need for our LCD? In order to be divisible by all of these denominators, we're going to need a factor of R. We're also going to need an R1. We're going to need an R2, and we're going to need an R3. So that would be your least common denominator of all your denominators. What I'm going to do now is multiply both sides of my equation by this least common denominator to eliminate all the fractions. As laborious as this step is, I would recommend that you do show it. So we're going to multiply everything on the left side and everything on the right side by our least common denominator. And the purpose of this is to get rid of all of the what? To knock out all the fractions. All right, now through cross canceling, we're going to eliminate every one of these fractions. Here, the R cross reduces out, and it leaves you with R1 times R2 times R3 times 1, which is R1, R2, R3. Equals, here the R sub 1 drops out with this R sub 1, leaving you with R times R2 times R3 times 1. Plus, here the R2 drops out, cross reduces out to 1s, leaving you with R times R1 times R3 times 1. Here the R3 drops out, leaving you with R times R1 times R2 times 1. And there you go. All right, now to solve for R3, the good news is we don't have any more fractions. The bad news is we're not done. I have to bring all my terms over to the left side of my equation that have a factor of R3. So to join this one, I'm going to have to bring this term over to the left and also bring this term over to the left. How do we do that? We will subtract these terms from both sides of our equation. Now, when I subtract these terms from the right side, of course, they drop out, leaving you with R times R1 times R2. And now, ladies and gentlemen, in my attempt to solve for R3, I'm going to have to factor R3 out of all three of these terms. So here's the R3. I pull it out of all three terms, and what do I have left? What I'm going to leave behind is what? When you factor it out of the first term, you'll leave behind R1, R2. Minus, when you factor it out of this term, you leave behind R times R2. When you factor it out of this term, you leave behind R1. Finally, to solve for R3, I have to get R3 by itself. So I'm going to divide both sides of my equation by this entire factor here. You got to divide the right side by the same thing, though. Oh, this way. That should be 2. There we go. This all drops. And therefore, we're left with R3 is equal to R times R1 times R2. And it's all divided by R1 times R2 minus R times R2 minus R times R1. And there you go, ladies and gentlemen. We have solved this formula for the variable or the resistance R3. Any questions how we went through and solved that formula for R3? Okay. All right, and to an electrical engineer designing a circuit, this may be necessary to solve for one of the resistances to make sure that it's within tolerance. So it means something to an electrical engineer. To us, we're just trying to solve this formula for a variable called R3, and we have done that. Okay. No, we did not do the classwork yet. No classwork yet. Okay. All right. Now this next formula here pertains to the time it takes for a pendulum. The time it takes for a pendulum to basically go through one swing. So if you envision like a grandfather clock, you have like a pendulum here, and this thing, you know, swings back and forth. Okay. Grandfather clock, right? Back and forth it goes as it keeps time here. T stands for time. S stands for the length of this arc that is swept out by the pendulum bob. That's called the arc length. Okay. And G is the acceleration of gravity. So ladies and gentlemen, I want to take this formula, which is presently solved for time t, and suppose I want to solve it for the arc length. I want to solve it for S. So how would we solve this formula for S? Anybody want to weigh in as to what we could do first here to try to solve for S? How could we solve for S?
Would you have to multiply something?
Yeah, I'll give you a hint. How can I get rid of that square root there?
Yeah, can you square both sides?
You know, let's knock the square root out. Let's square both sides of this equation. That kind of gets our variable S out of jail, so to speak, gets it out from underneath the square root. That's what we want, because we've got to solve for S. So therefore we have t squared is equal to, now when you square a square root, both the square root and the square disappear. They undo each other. And it just leaves you with 2S over G. All right, now how would I solve for S? Looking a lot better now. Now we got S out from underneath that radical. How would we solve for S?
Multiply by G.
Multiply both sides of the equation by G. And when you multiply the right side by G, of course, the G's drop, leaving you with 2S. And then finally, we do what? Divide both sides by 2. And therefore, we have solved for the length of the arc. Therefore, we will have solved for the length of the arc that the pendulum bob carves out as it oscillates back and forth, keeping time. And there you go. We solve for the arc length in terms of time. Okay. So solving formulas, like I said, is a pretty important task. If you get in any sort of computational field, you're always working with formulas. Engineering has loads of formulas to work with. Even in nursing, dosage calculations, nurses have to be aware of formulas, such as there is a formula for the BMI, the body mass index. Okay, there's a lot of formulas in the health field. Okay. So you have to know how to, from time to time, manipulate these formulas and solve them for a particular variable. Computer programmers have to know how to do this too. In order to present a formula to a computer system, sometimes they have to solve it for a particular variable first. Okay. So there's quite a bit of math going on. All right, ladies and gentlemen, classwork number 1. I'll have you try a couple here. We'll call this classwork 1. Today is Groundhog Day, by the way. Happy Groundhog Day. Hopefully we have a short remaining winter, but I don't know if the groundhog accurately can predict that. I wouldn't bet my life on that. I would say it's 50-50. Okay, over the long haul. 6 more weeks of winter. Son of a gun. Is that what Phil said? Okay. Well, we're in for a long one. All right, let's try this one. I'll have you try this one here. Try to solve this this equation here. Ladies and gentlemen, your hint for this one is to use a U substitution. Notice the leading power 1/2 is twice the middle power of 1/4. 2 times 1/4 gives you 1/2. So this is quadratic in form, this equation. So you should be able to use a U substitution to reduce it down to a quadratic equation in a variable U. Here's a further hint. Let U be equal to the middle variable, y to the 1/4. See if you can utilize a U substitution to solve that equation. All right, try that one there. And what else we got here? And I'll have you work with this one. I want you to try to take this formula here and solve it for V2. Here is the formula. See if you can solve this formula for the variable V2 right there. Okay. Now we'll call that classwork number 1. See if you can do something with that. All right, did anybody by chance get the solutions to problem number 1 and feel confident to share them with us? All right, so we're gonna do a U substitution on this first equation here. I'm sorry, did somebody? I missed the chat there. Let me see what it says here. All right, any remaining questions from anybody? What is it, Natalie and Piper? Any remaining questions? If not, I'm going to sign off so I can start compiling this video. You have a great weekend.